Okay. Good morning, everyone. So I'm not here today, clearly. So we're going to do a video lesson just like the last time that I was away. It's not too long of a lesson, but it is a new formula. So yesterday we did independent events. Today we're looking at dependent events. So what that basically means is the probability of an event happening only if something else has already happened, essentially. So I'll read through the little blurb at the top, what the formula means, and then we'll run through a couple of examples. So it says, if the outcome of an event B depends directly on the outcome of another event A, the events are said to be dependent events. The conditional probability, that's what we call it. So the second event that depends on the first is called the conditional probability of B, is denoted as P, so the probability of B given A. So that line means given. So the probability that event B will happen given that event A has already happened. And that is the probability that B occurs given that A has already occurred. So basically what I just said. Okay, so the product rule, which if you're a functions person, product rule just essentially is multiplication. For dependent events looks like this. So if A and B are dependent events, we will still multiply probabilities to find the probability that both happen. However, we must use the conditional probability for the second event. So what we're used to doing is the probability of two events happening. We do the probability of A times the probability of B will give you the probability that both happen. However, this time they're giving you a conditional probability. So this time we must use the conditional probability for the second event. So the probability that both events will occur is given by the product rule for dependent events. So the probability that A and B occur, so the intersection, equals the probability that A occurs times, because it's and, the probability that B occurs given that A has already occurred. Okay? So a rearrangement of this, depending on what you're given in your question, if we already know what the probability of A and B taking place is, we can arrange the formula that's up here and find the conditional probability. So it's basically isolating the probability of B given A. Okay, so we'll run through an example. So here it says, I'm just going to shift the camera a little bit. Okay, so here it says the probability that Pat will go to York University is 1/5. If Pat goes to York, then the probability that her boyfriend, Jerry, also goes to York is 3/4. What is the probability that Pat and Jerry attend York University? So this probability, the difference between what we've normally been doing and what we're doing now, this probability is not just Jerry's probability of going to York. It's Jerry's probability of going to York if Pat also goes. Jerry could be 25% sure that he wants to go to York, but if his girlfriend goes, then he is 75% sure that he wants to go to York. So this is the conditional probability. Okay, so just like normal, we need our let statements. So we're going to say, let A be the event that Pat goes to York. And then let B be the event that Jerry goes to York. Okay, now there's a couple things in here that we know. We know that the probability that Pat goes to York, so probability of event A, is 1/5. We also know that the probability of event B happening, so we know the probability that Jerry goes to York given that Pat goes to York, so the probability of event B happening given that A has happened, is 3/4. We need to find what is the probability that Pat and Jerry attend York. So we need to find the probability of A intersect B. Okay. So obviously we're going to, since we're solving for this, we're going to use this formula here. So we have probability of A intersect B equals the probability of A times the probability of B given A. Okay, so then from here we just plug in what we know. Probability of A is 1 over 5 times probability of B given A is 3 over 4. You do the multiplication, tops with tops, bottoms with bottoms, and you're going to get 3 over 20, which tells us that there is a 15% chance both Pat and Jerry attend York U. Okay? So that's that question. So that's the use of the conditional probability using the original, not the rearranged equation. Okay, so now we're going to jump to the back. This one brings into play that table that we made with when 2 die are rolled and we get our 36 possible different sums. So it says, what is the probability of rolling a sum greater than 7 with 2 dice if it is known that the first die rolled is a 3? So basically we're saying, okay, we're rolling 2 dice. The first one has to be a 3. If the first dice is a 3, what are my chances that my second dice rolled will give me a sum greater than 7? So we're going to say let A be the event of rolling a sum greater than 7. And let B be the event that the first die rolled is 3. Okay, so let's figure out what our possible sums could even be. So this is where I said that table comes into play. So I'm going to draw one here. Yours will probably look a little neater than mine. And this can represent dice 1. This can represent dice 2. And I'm not going to fill in all of them. I'm just going to start maybe from here. So this one's 7. And then we'll have sum of 8, 9, 10, 11, and 12. Now we want sums greater than 7. So 8, 9, 10, 11, or 12. I will also get 8 with 5 and 3. So right here. And then I'll get 9, 10, 11. I'll also get 8 with 4 and 4 right here. And that's going to be 9 and 10. I'll also get 8 with 3 and 5. So right here. I'll get 8 with 2 and 6 over here. And then 1 and 6 would give me that 7, which obviously that one does not count. So we can see that all of our possible sums that are even greater than 7, they lie right here. Those sums are all greater than 7. Okay? But we need to make sure that the first die rolled is a 3. If the first die rolled is a 3, then based on what my second die rolled is, okay, so 3 and 1, all of these would not give me a sum greater than 7. So the only ones that would give me a sum greater than 7 if my first die rolled is a 3 is if I roll a 5 next or if I roll a 6 next. Okay? So now let's figure out a few things. So we have the probability of A given B. So the probability that we roll a sum greater than 7 given that we've rolled a 3 with the first die, because this time we're looking for the conditional probability, okay, is the probability of A and B happening over the probability of B happening. This is what we don't know. So now I'm going to jump here and I'm going to say, okay, well, we can figure out the probability of A and B happening. We can figure out the intersection. The probability that A intersect B happens is the number of ways that this thing can happen over the number of total possible outcomes. There was only 2 ways event A and B could happen out of the total 36 possible sums. Okay? And then we also know the probability of event B. The number of ways that the first die rolled as a 3 is 1 out of 6 ways, right? There's only 1 3 on a 6-sided die. And now we have everything we need. So we can say, therefore, the probability of A given B is equal to the probability of the intersection. Now this can be reduced here. 2 over 16 can be reduced to 1 over 18. So we get that this equals the probability of the intersection, which is 1 over 18, over the probability of B, which is 1 over 6. Now when we have a fraction over a fraction, we can take our fraction on the denominator, flip it, and multiply. So we get 1 over 18 times 6 over 1. And that will simplify to 1 over 3, which will give you 33.33%, which is low. Okay, so there's a 33.33% of rolling a sum greater than 7 with 2 dice, given the fact that the first die rolled has to be a 3. Okay? Now, I have time limits on these videos, so I'm going to do the last question in a separate video. Okay?